Hello friends, welcome back into the class. The today's topic is FMO theory. Already we discussed. Today's topic is PMO theory of electrocyclisation reactions. So the PMO theory, also called as perturbation molecular orbital theory. So what is perturbation molecular orbital theory? So here perturbation molecular orbital theory, also called as aromatic transition state theory. So we are going to discuss about purely the nature of transition state. So that's why here we are calling aromatic transition state. So it was proposed by Evans, Zimmermann, Dewar. So therefore it is also called Dewar-Zimmermann theory or Dewar-Zimmermann model. So in this theory, in FMO theory, we purely select about HOMO and LUMO orbitals, but in this theory you can select any molecular orbital, that means psi1, psi2, psi3, any molecular orbital to explain the allowed conditions of given pericyclic reactions. That's why we are calling this theory as perturbation of molecular orbital theory. So why we are calling perturbation? Because you can select any molecular orbital to predict the reaction condition. So but we always use it to take psi1 molecular orbital because it is easy to draw, to give the signs psi1, because all lobes are having plus sign at the top side, minus sign at the bottom side. So therefore it is very easy. So that's why we are taking psi1 molecular orbital, and then we are going to classify the transition states into aromatic and anti-aromatic transition state. So that means here this theory purely concentrate on aromatic and anti-aromatic transition state. That's why it is calling aromatic transition state theory. So here you know that always, so when the reaction is taking place at a normal condition, that means under heating, the pericyclic reaction takes place either thermally or photochemically. So heating, the heating energy always less than photochemical energy. Always photochemical energy is present in high quantity. So that's why the activation energy of thermal reaction is lower than photochemical reaction. So you see this point. So aromatic transition state, activation energy is smaller than anti-aromatic transition state. So because this is anti-aromatic transition state, friends, anti-aromatic transition state. So that means aromatic transition takes place under thermal condition, where anti-aromatic takes place in photochemical condition. Why? Aromatic transition state required less activation energy, where anti-aromatic required more activation energy. That's why aromatic transition state reactions thermally allowed, anti-aromatic transition state reactions are photochemically allowed. So this is the basic concept. So here just you focus on what is perturbation molecular orbital theory. It is also called aromatic transition state theory or Zimmermann-Dewar model theory. So in examination they are asking explain the pericyclic reactions based on perturbation molecular orbital theory, or simply they are asking PMO theory, or simply they are asking aromatic transition state theory. Sometimes they are asking Dewar-Zimmermann theory also. Okay, so let's better. So we already know that the perturbation molecular orbital theory is working on the nature of transition state. So what is the nature of transition state? That means whether the transition state is aromatic or anti-aromatic. The classification we are going to discuss. So you take the cyclic transition state because pericyclic reactions always proceeds through cyclic transition state. So here in cyclic transition state, the number of nodes are even or zero. Number of nodes are even or 0, that is called Huckel transition state. That is called Huckel transition state. What is Huckel theory? So Huckel theory is when any planar compound having 4n plus 2 pi electron, that is called aromatic. So why we are recalling this concept? So because, yes, next here, if number of nodes are odd, then that is called Mobius transition state. What is Huckel transition state? Number of nodes are 0 or even, Huckel transition state. Number of nodes are odd, Mobius transition state. So what is Huckel rule? Huckel rule is 4n plus 2 rule. So when the compound has 4n plus 2 pi electrons, that is called aromatic compounds. Okay, let's see. So when the transition state belongs to 4n plus 2 pi electron system, that means in the reactant, if it has odd number of pi bonds, that is called 4n plus 2 pi electron system. So now this is called Huckel rule related, therefore this is called Huckel aromatic transition state. Huckel aromatic transition state. When it has 4n pi electrons, according to Huckel rule, when the compound has 4n pi electrons, that is called anti-aromatic compound. That's why this is called Huckel anti-aromatic compound. You see this branch, when cyclic transition state has 0 or even number, that is called Huckel transition state. If this transition state has 4n plus 2 pi electron system, belongs to 4n plus 2 pi electron system, that is Huckel aromatic. If it belongs to 4n pi electron system, Huckel anti-aromatic. Similarly, Mobius transition. Okay, so when you heard about aromatic, that is thermally allowed. When anti-aromatic sound is there, then that is photochemically allowed. So now come to this branch, it is reverse to this branch. That means, yes, when compound is belongs to 4n plus 2 pi electron system, in Mobius theory, that is called Mobius anti-aromatic compound. When it has 4n pi electron, that is Mobius aromatic. Reverse, just reverse. Right, when the sound anti-aromatic is there, that is photochemically allowed. Mobius is thermally allowed. Aromatic is thermally allowed. So this is the flowchart we have to remember to explain the PMO theory. Okay friends, right, simply what you have to do, so you just first select the psi 1 molecular orbital. Which molecular orbital? We have to select psi 1 molecular orbital because it is very easy to representation. Then we have to show, yes, cyclic array of atomic orbitals in transition state. That means we have to select the transition state, then classify the transition state aromatic or anti-aromatic. How you are going to classify that? You see, when compound has 0 or even number of nodes, 0 or even number, that is called 0 or even number of transition nodes, the system belongs to 4n pi plus 2 pi electron system, that is called Huckel aromatic transition state. Simply you see, 0 or even number, Huckel system, 4n plus 2, that is aromatic. When it is belongs to 4n pi electron system, that is Huckel anti-aromatic. Aromatic transition state always thermally allowed, anti-aromatic always allowed photochemically. And see, yes, aromatic transition state thermally allowed, anti-aromatic is a photochemical allowed. You see that if odd number of nodes are present, obviously odd number of nodes are present, that is called Mobius system. 4n plus 2 pi electrons are present. In Mobius system, 4n plus 2 belongs to anti-aromatic, Mobius anti-aromatic. When 4n pi system, that belongs to Mobius aromatic. Aromatic system is thermally allowed. Already here you did it. Anti-aromatic is photochemically allowed. So friends, this is about the fundamental basics we have to remember for PMO theory. Let's explain 4n pi electrocyclisation reactions based on PMO theory. So the reaction sorry, 1,3-butadiene, yes, this bond shift here, yes, this bond shift here, the bond shifting here we get a sigma bond, the bond shifting here, we get a new pi bond. So 1,3-butadiene forms a cyclic transition state. This is converting into cyclobutene. So first, Kahn mode of rotation in ring closure reaction, ring opening reaction. So here I am taking psi1 molecular orbital. You can see this is psi1 because all lobes are positive at the top side, negative at the bottom side. So this carbon at this orbital, Kahn rotation, you have to rotate in clockwise direction or anti-clockwise. If you are rotating to clockwise here, again you have to rotate, this is also towards clockwise only. So the both terminals are rotating to clockwise direction. You see both terminals are rotating to clockwise direction. That is called Kahn mode of rotation. You see, when you, so I am not completely rotating, just partially rotating, just partially. So just slantly I am going to, so this is the molecular orbital present like that. Here I am going to rotate like this. So when you are going to rotate horizontally, this is going to form a sigma bond. You should not rotate like this, just slantly rotate. So this orbital and this orbitals are slantly rotated. First connect all above side lobes. Here this is above side, this is above side, this is above side, this is above side. So by using a dotted line. Now after the rotation, you can observe that this plus lobe is going to interact with minus lobe because these are going to contact with each other. Yes, connect to those two. Now identify number of nodes. Here plus, connected to plus, connected to plus, connected to plus. This is over. Here this is the minus. Plus minus is, this is belongs to only one orbital. You cannot say here node is there. So when, if you want to identify node, that is in between two orbitals. Okay, so plus and minus, that's why here node is present. How many nodes? So this is cyclic transition state, node is present. So here what is the system? 4 and pi system, because 2 pi bonds are there, even number, 4 pi system. So here number of nodes are 1, that is odd. When number of nodes are odd, that system is called Mobius system. In Mobius system, 4 and pi belongs to aromatic. Mobius aromatic. When the aromatic word is there, that is thermally alert. Okay friends, this is about Kahn mode of rotation. In a ring closure reaction, let's see ring opening reaction. This is the sigma bond and this is, so you can take any kind of signs, no problem here. You take minus, plus, plus, minus, minus, plus, no problem at all. You can easily explain by taking any orbital. For easy convenience, I am taking like this. Okay, here, so again this orbital rotating in clockwise direction. So this orbital is also rotated clockwise because we are discussing about Kahn mode of rotation. You see at both terminals we are rotating in clockwise, Kahn mode of rotation. So when you rotate this slightly, just slightly you rotate the orbital. So here we get this orbital and this orbital position is obtained like this. So connect all above side lobes, minus, plus, plus and plus, because these are present at the top side. Okay, right before the cleavage you can observe that plus is connected with plus, this plus is connected with plus. Yes, before the cleavage. So now identify the nodes. Here you see plus plus connection, plus plus connection, plus plus connection, here plus minus connection. So in cyclic transition state you can observe one node here. So what is the system belongs to? 4 and pi system, because 2 pi bonds are there. Number of nodes are 1, odd number. When odd number nodes are present, that is called Mobius system. In Mobius system 4 and pi belongs to aromatic. So when aromatic is there, that is thermally allowed. So friends, Kahn mode of rotation for 4 and pi electrocyclizations, so thermally allowed. Let's see, yes, this mode of rotation. Yes, this mode of rotation. Again I am going to select a psi1 molecular orbital. So in psi1 molecular orbital, this lobe is rotating to clockwise. So therefore you have to rotate this lobe in anti-clockwise. If you take this is anti-clockwise, then you have to rotate this is clockwise. In this mode of rotation, one orbital rotate in clockwise, another orbital rotate in anti-clockwise. So therefore, so both orbitals are rotated in opposite direction. Yes, that's what is called this mode of rotation. Okay friends, after the rotation, so I am rotating this orbital towards clockwise directions slantly, and this is also rotating in anti-clockwise slantly. Now connect all top side lobes. Yes, these, right. So after the rotation, you can observe these two lobes are going to be connect, then connect those two. So now this is the transition state. So plus connected to plus, plus connected to plus, plus connected to plus, plus connected to plus. That means the system is 4n system, number of nodes is equal to 0. When number of nodes are 0 or even, the system is called Huckel system. In Huckel system, if it has 4n electrons, that is called Huckel anti-aromatic. When the word anti-aromatic you written there, that is photochemically allowed. So friends, it is very easy theory to explain, so you should not get confused. If you get confusion, then the complete question get be wrong. Okay, now you see ring opening reaction. Yes, this is the molecular orbital, which is the closed system. Now this orbital rotated in clockwise, this is rotated in anti-clockwise. So you see both orbitals are rotated in opposite direction. Therefore this mode of rotation, you rotate slantly this orbital and this orbital. You connect all top side lobes first. Yes, before the cleavage, this plus is connected to plus, therefore connect to these two also. So now you see at number of nodes, and the system is 4n system. Yes, here minus after plus, here one node is there. Yes, one node is present. So sorry, it is two nodes are present. I written one node wrongly. So here one node is present, here also one node is present. So here there is no node, two nodes, that is Huckel system, and 4n Huckel anti-aromatic, that is called photochemically allowed. Friends, this is about 4n electrocyclisation reactions explained by using PMO theory. Let's explain. Yes, 4n plus 2 electrocyclizations. In 4n plus 2 electrocyclizations, we are taking 135 hexatriene. So this 135 hexatriene, this bond shift here, we get a sigma bond, and this pi bond shift here, we get a new pi bond, and this pi bond shift here, we get another new pi bond. So let's see first Kahn mode of rotation. Again we are selecting psi 1 molecular orbital of S135 hexatriene, right. You rotate this orbital in clockwise direction. Here this orbital is also rotating in clockwise. So both are rotating in clockwise, therefore it is called Kahn mode of rotation. So after the rotation of these orbitals slantly, we get this type of system. Now connect all top side lobes. Yes, so all top side lobes are connected. Now after the rotation, you can observe this lobe is going to connect with this lobe. Yes, and you see number of nodes. This is cyclic transition state, and here you can observe one node is present here, because top side all lobes are plus. Here plus is going to connect with minus, therefore the system is 4n plus 2 pi electron system. And number of nodes are 1. When one node is present, that is called Mobius system. And Mobius 4n plus 2 is anti-aromatic, that's why it is photochemically allowed. Kahn mode of rotation for 4n plus 2 pi electrocyclisation, photochemically allowed. You can also explain for ring opening reaction. So this is the sigma bond and these are the pi bonds. So these pi bonds. Okay. So right, the first orbital is rotating in clockwise, the second is also rotating in clockwise direction. So that's why it is Kahn mode of rotation. So after the rotation slantly, yes, so just slantly rotation, so we get this system. Now connect all top side lobes, yes, all top side lobes, and before the bond cleavage, plus is connected to plus, yes, right, plus is connected to plus. Now you observe, this is a cyclic transition state. Now the system belongs to 4 and pi system, yes, and number of nodes are here, plus minus are connected. Are you observing here, dots are there, so therefore number of nodes are 1. So when one node is there, that is Mobius system. In Mobius system, if you have 4 and pi electron, that is anti-aromatic, therefore it is photochemical, so sorry, this is not photochemically allowed, this is a photochemically allowed. Okay, so now let's explain this mode of rotation. So psi1, yes, now this orbital is rotating in clockwise direction, so this should rotate in anti-clockwise, so therefore one is clockwise, another one is anti-clockwise, this rotate. So you rotate those two lobes slantly, so connect all top side lobes, yes, right. So after the rotation, these two lobes are going to connect. So now you can observe, in transition state there is no nodes, and here also the system belongs to 4 and plus 2 pi electrocyclisation reaction. Number of nodes are 0. When 0 nodes are present, that is called Huckel system. Huckel system contain 4 and plus 2 electron, that is aromatic transition state. Aromatic means thermally allowed. You can also explain the same concept to ring opening reaction. This is rotated in clockwise, this is rotated in anti-clockwise. So now, right, so slant rotation, these are orbitals. So connect all top side lobes, yes, so all top side lobes are connected. Before the cleavage, these two lobes are connected and connect to these two. Now you see, plus minus connected here in transition state, so plus minus, so therefore these two are the nodes. So the system is 4 and plus 2 pi electrocyclisation system, nodes are 2. When number of nodes are 2, so then this is a even number of nodes, Huckel system. In Huckel system, 4 and plus 2 pi electrons are present, that is Huckel aromatic. Huckel aromatic is thermally allowed. That means for 4 and plus 2 pi electrocyclisation, Kahn rotation is photochemically allowed, this rotation is thermally allowed. So let's explain Woodward-Hoffmann selection rules. So electrocyclisation, mode of rotation, nature of transition state, and allowed condition. 4 and pi electrocyclisation. You take Kahn rotation. In Kahn rotation, so in previous case you can see there, what is the transition state obtained? Mobius aromatic transition state. So therefore thermally allowed. So in this rotation, the transition state is right, that Huckel anti-aromatic transition state. That's why photochemically allowed. For 4 and plus 2 pi electrocyclisation, Kahn rotation. In Kahn rotation, the transition state is Huckel anti-aromatic transition state. So photochemically allowed. This rotation, you got Huckel aromatic transition state, thermally allowed. So this is the Woodward-Hoffmann selection rules. After explaining the pericyclic reactions by using any theory, you have to write Woodward-Hoffmann selection rules. Friends, so this is about PMO theory of electrocyclisation reactions. So we will meet in